Hello everybody, welcome back. This is Jonathan Gardner. We're covering Sergey Lang's basic mathematics, and now we're on section 11.2. 11.2 covers sine and cosine, which can be a very scary concept the first time you run into it. It's really not that difficult. I'm going to take a slightly different approach to the concept of sine and cosine than the book does, but we'll get right back to the book, so I'll explain what the book is trying to explain. So sine and cosine come from the fact that when we have a point in the plane, let's say it's at A comma B, then we notice that through that point there's a ray. Let me draw this ray using a different color. Let's use this green color. There's a ray that goes from the origin through that point and off into infinity, right? So we notice that that ray forms an angle with the positive x-axis. So this axis over here, there's an angle there, and we're going to call that angle theta. Okay, theta is just a Greek letter. That's all it is. So in Greek, they have alpha, beta, gamma, delta. They're different letters. We're using theta just because we've kind of run out of Latin letters, so we're going to use Greek letters now. So theta. And the way you draw theta, if you haven't drawn a theta before, is you just draw a circle, and you put a line through it, and that's theta. Okay. And this is lowercase theta. The capital theta, which you probably won't see, it has like an H in the middle like that. Anyway, we're using theta to represent angles. In this book also he'll use capital A to represent the measure of the angle as well. Anyway, so we notice that there's the coordinates A comma B. We notice also that there's angle theta that forms from the ray that goes through that point from the origin and the x-axis, like this, okay? And there's also, we can consider the distance here, we'll call this distance r, okay? So we can represent this point as, we call this Cartesian or rectangular coordinates. We can also represent it as a combination of these two numbers. And these two numbers we'll call polar coordinates. Okay? And these two numbers we'll call Cartesian or rectangular coordinates. Okay. All right, and the second question is, can we describe all the points in the plane with these polar coordinates? The answer is yes. You can imagine that you can draw given any measure of an angle here, theta, between 0 and 2 pi. Remember, we're using radians now. So as long as theta is less than or equal to 0 and is less than 2 pi, because 2 pi would be the same as 0, then we can use any value of r from 0, which would be the origin, out to infinity or whatever we want to do, and we can describe every single point in the plane this way. So what sine and cosine are going to do is allow us to combine these two concepts together into one. We're going to relate the angle with the rectangular coordinates. All right, now the next thing is, what are sine and what are cosine? So if we have a unit circle, and it doesn't matter what length you choose, you just define that length, the radius of the circle, to be 1, okay? Then every point on this circle, A comma B, is actually the same as, we're going to say, cosine of theta, sine of theta, okay? And so we're going to draw, remember, this is the unit circle. We're going to have the ray that goes through, and this is going to form an angle theta. Okay? So A comma B on this unit circle is going to be cosine of theta, comma sine of theta. So sine of theta represents the vertical distance from the origin. Okay? So when we're on the top here, let's kind of draw a little line across here. This sine of theta is going to be greater than 0, and down here sine of theta is going to be less than 0. And then for the cosine, which is the x-coordinate, this side cosine of theta is greater than 0, and over here cosine of theta is less than 0. And obviously here we have cosine of theta equals 0, and here we have sine of theta is equal to 0. So that's kind of the way that I think of this. Now, another really useful thing, and he doesn't talk about this in the book, but this is something that's very important. It's going to come up time and again in physics. We're going to use it over and over again. If you consider a very small angle, so let's use a protractor. Let's use a straight edge actually. So this protractor will do. So we're going to draw a very small angle. Okay, so we have that, and then we're going to go very small angle. Okay. So we're talking like a tiny angle. Okay. And if you look at this angle and you consider that this is the distance r, and this is also the distance r, practically. It's not quite the distance r. But what is the vertical component of this? Well, that's going to be sine theta. Okay, but because the vertical perpendicular part is so close to the actual arc length, the sine theta is actually going to be, I'm going to put a little tilde on top, it's almost equal to theta for very small angles. And you might wonder, like, what do I mean by small angles? Well, I think if theta is less than about 1/10, then sine theta is going to be the same as theta within 10%. That's roughly the measure that we can think of. And this small angle approximation for sine theta is universally useful when you're doing physics and stuff like that. It's going to come back again and again and again. So we'll just remember this. If you forget which is which, just remember sine theta is, when theta is very small, sine theta is practically the same as theta. All right, now let's go through the content and the way the book presents it. Okay, so he starts off and he says we have a coordinate system. Okay, so we have a coordinate system. Excellent. And then we're going to draw an angle A with a vertex at the origin O. So we're going to have here, and we're going to have the angle A. So instead of theta, he's using A. So this is the origin O here. Okay. We select a point A comma B that's not on O. So we're going to take a point here. We're going to say this is A comma B. Okay. And we note that we have this distance r here. So A comma B, basically if we drop down, what that means in the coordinate system is you go A to the right and you go B up, right? So we're going to have r squared is equal to A squared plus B squared, or if you want to write it out this way, it's the same thing. Okay, remember when we take the square root, it's always going to be positive. All right. And then he defines, he says sine of A is equal to B over R. So the y component divided by R, which is going to be over the square root of A squared plus B squared. And then he's going to define cosine of A to be A over R, which is A over the square root of A squared plus B squared. Okay, this is a very good general definition. Okay, suppose we selected another point along this ray. So we're going to choose this point up here. We're going to call this A1, B1, A1, B1. Okay, so the distance from here up is B1, and the distance from here over is A1. Okay, and then we're going to have a new distance. I think we're going to call it, I'm going to call it R1. So the distance here is going to be called R1. So we have obviously that R1 is equal to the square root of A1 squared plus B1 squared. We're using Pythagorean theorem. Okay. And we note also that we can find some constant C such that if we start with A and we multiply by C, we will get A1. And by using that same constant, we multiply B and we get B1. And in fact, it's going to work for the radius as well. Okay. All right. And if you need to convince yourself that this is true, you can calculate for yourself how these things relate to each other. I'll just kind of, in the margins here, I'll do what he does. He starts with this. He says that, note that your B1 over the square root of A1 squared plus B1 squared is the same as C times B all over the square root of C times A squared plus C times B squared. Okay, that's going to give you C squared A squared and C squared B squared. You can factor out the C from the denominator, so you get CB all over C times the square root of A squared plus B squared. Okay, and so these two cancel, and you'll see that B1 is equal, B1 over A1 squared plus B1 squared is equal to B over A squared plus B squared. Okay, so those are the same. That ratio of the vertical component to the radius, the distance here, is the same as long as you're on this thing. So this angle, as long as it remains constant, you'll have a consistent and constant relationship between the vertical axis and the distance from the origin. And the same will hold also for the horizontal axis. Okay. If we were to choose the distance such that r is equal to 1, then sine of A would just be B, and cosine of A would just be A, right? So if the distance is just 1, so that would have to mean that basically A squared plus B squared is equal to 1. So we call that the unit circle. So if I were to draw a unit circle, let's use a different color here. Let's use this red. A unit circle that passes through that point such that this distance here is 1, okay? Then the cosine and the sine are just the y coordinate and the x coordinate. That's all it is. Very simple, okay? All right. Now, what if we go outside of that first quadrant and into another quadrant? So let's look at the second and third quadrants. So let's draw an axis up here. Let's say we have the ray going off this direction. So our angle A here is larger than pi over 2. So A is greater than pi over 2, but A is also less than pi, okay? In this case, we still have the same relationship. Sine A is equal, we have the point over here, we're going to call it A comma B. Okay, sine A, and if we consider that this is the unit circle, so the distance is 1, is still 1, is still A. And cosine A is equal to B, but notice that A is greater than 0 because we're in the top half of the quadrant, but B is less than 0. Okay, so cosine is negative, while sine is still positive. Okay, and if we were to go with an even greater angle, measure A, so now we have A is greater than pi, but A is less than 3 pi over 2. Okay, and in this case, our sine of A is that A is the B, I'm sorry, this is B, this is A. Our sine of A is the B, the vertical component, which is greater than 0, and the cosine is the horizontal component, which is less than 0. And in this case, in this quadrant, sine of A is going to be B, which is less than 0. It's below the vertical axis. And cosine of A is going to be A, which is also less than 0. Okay, so both are negative. So we have a point here, A comma B, radius 1 away. And you can figure out what happens in this coordinate, this quadrant as well. Sometimes people like to remember sine and cosine in terms of a right triangle. So we take a right triangle, one of the angles is 90 degrees, and we call this side the hypotenuse, right? We're going to use this angle here, theta, and so this will be the opposite side, and this will be the adjacent side. So in this case, sine theta is going to be the opposite, the length of the opposite side over the length of the hypotenuse. And cosine theta is the adjacent side over the hypotenuse. This is typically how sine and cosine are first introduced, but I don't find this particularly useful. Very rarely do I think of sine theta or cosine theta in terms of a triangle. I usually think about it in terms of polar coordinates. What about all possible values of theta? Right? So we typically think of 0 is less than or equal to theta is less than 2 pi. But what if this is not true? Remember that we can typically take radians and rewrite them. We can say if the angle theta is equal to 2n, where n is some integer, times pi, so basically 2 pi times n. And then we have plus w, but w itself lies within that range where it's less than 2 pi and it's greater than or equal to 0. Then we can typically rewrite, so we can say cosine of theta is the same as cosine of 2 pi times n plus w, which is the same as cosine of w. And then sine of theta is a sine of 2 pi times that integer plus w, which is equal to sine of w. Okay, and what this means is, suppose theta, let's say theta is equal to 7 pi over 2, right? So 1, 2, 3, 4, 5, 6, 7. So we're going around twice. Once, and we go back here. So this is theta equals 7 pi over 2. Well, if we were to subtract 2 pi from that, which would be 4 pi over 2, we would get W is 3 pi over 2. And since this represents the same angle, then we would believe that cosine of theta has to equal cosine of W, and sine of theta has to equal sine of W. Okay? So when you have numbers that go outside of the range, you can just add 2 pi's as necessary or subtract them as necessary to get to an angle measure that is within 0 and 2 pi, and then solve it that way. Okay? Let's calculate sine and cosine for some values. This might seem complicated or difficult, but really it's not. Okay? So let's draw a little table over here. So we're going to have theta, we're going to have sine of theta, and we're going to have cosine of theta. So when theta is 0 degrees, 0, not 0 degrees, 0 radians, and sine of theta is going to be 0. The vertical component is 0, and cosine is going to be 1. And why do I know that? Well, if we think of this, theta of 0 is it's going along here. So any coordinate along here is going to have something for the x component. We're going to put b, a, comma, 0, but 0 for the y coordinate. And we also have pi over 2. That's 90 degrees. So the sine theta will be 1, cosine theta will be 0. Okay? And then we can also calculate for pi. Pi is when we go a full 180 degrees. Okay, so sine theta will be 0 and cosine will be minus 1 because the x is in minus 1. And then we have 3 pi over 2. So we're going all the way around down here. So sine theta is minus 1 because we're below the axis, and 0 for the x coordinate. Okay. What about 45 degrees, or pi over 4? In the case of pi over 4, this is what we get. We're going to get the same distance here as here. And then this is going to be 1, right? So sine theta is going to equal cosine of theta. So I'll put pi over 4. They're going to be the same. And we know that they have to add up, right? So 1 is equal to the square root of 2a squared. So 1 is equal to the square root of 2 times a. So a is equal to 1 over the square root of 2. If we multiply the top and bottom by square root of 2, then we're going to get the root of 2 over 2. Okay? If we take pi over 6 and pi over 3, pi over 6, that would be 30 degrees. And pi over 3 would be 60 degrees. Okay, this is a little bit more involved to calculate. Let's go ahead and draw out what that would look like. So we're going to have a triangle like this, and this would be pi over 3. This would be pi over 6 up there, and then we have the radius 1. And if we take this and reflect it through, so we have another triangle on the other side, then we notice right away that this angle here is also pi over 6, this angle is pi over 3, and now we have a triangle that's equilateral. So this side must be 1/2, and this side must be 1/2. Okay, so sine would be the opposite. Sine of pi over 6 is going to be 1/2, and cosine of pi over 3 is going to be 1/2. Okay, now the question is, what's that distance there? Right? So what we can do is we can say 1/2 squared plus b squared times square root has to equal 1. Okay? And so we get, if we work this through, we get square root of 1 over 4 plus b squared has to equal 1. Well, this isn't very, let's square both sides. So we have 1/4 plus b squared equals 1. B squared equals 1 minus 1/4, which is going to be 3 over 4. So b is going to be root of 3 over 2. So that's the other value, root of 3 over 2, root of 3 over 2. So memorize these. 0, 0, 1, pi over 6, 1/2, root of 3 over 2, pi over 4, root of 2 over 2, root of 2 over 2, and then pi over 3, root of 3 over 2, and then 1/2, and then pi over 2 is 1, 0. So there's a progression here for these angles. 0, 1/2, root of 2 over 2, root of 3 over 2, and then 1. All right? And these are typically the ones that you'll see on your homework assignments, especially when you're first doing trigonometry. When you're doing more advanced mathematics, you won't run into these very often, but when you do, it's a pleasant relief. Okay. Notice, according to Pythagorean's theorem, that r squared is equal to a squared plus b squared. And if we take r to be 1, then we have 1 is equal to a squared plus b squared. Well, if we have sine of theta is equal to b and cosine of theta is equal to a, then that means 1 is equal to cosine squared theta plus sine squared theta. And we write it this way, but really this is kind of confusing. So what this means is we take cosine of theta, and whatever that is, we square it. And then we take sine of theta, and whatever that is, we square it. That's what these two symbols mean. We typically write it this way. I know that it's confusing for beginners, but that's what we do. This is one of the many trigonometric identities that you'll have to memorize. Okay, this one is simply just Pythagorean's theorem. There's no complexity at all for this one. There are additional ones that are very useful that we will find very quickly here. Theorem 1 in this chapter states the following. It says for any number x, cosine of x is the same as sine of x plus pi over 2. And sine of x is the same as cosine of x minus pi over 2. All right, this is another trigonometric identity that you'll have to memorize. How do we prove this? Well, let's draw out what that would look like. It's pretty easy to prove by graphical interpretation. So we have the interpretation here. We have a comma b is the point there. We have some angle theta, right? What would it mean to add pi over 2 to this angle? Well, that would mean you just take the right angle. So we're going to draw over here, and we're going to take this as a right angle, right? So theta plus pi over 2 is this big angle here, or x over pi over 2, really. This is x, not pi, theta, x. And then this angle here is x plus pi over 2, right? Okay. So we have this point here. Let's call this point Q. And then when we rotate by 90 degrees, Q is going to end up, Q prime over here, after rotating 90 degrees, is going to end up there. And you notice the distance to Q and the distance to Q prime is the same. Well, in this case, this is cosine, right? This distance here is cosine of theta. So cosine of theta is the same as sine of theta plus pi over 2. What about the sine? Well, that's this distance here. Well, when we're rotating this by 90 degrees, that distance will maintain the same, and so cosine is going to be the same as, well, let's go the other way. So we're going to go down here, we're going to take this angle here, we're going to subtract. So this angle here, this is x minus pi over 2, okay? And so if we take a Q double prime here, which is what you get after rotating 90 degrees the other opposite direction, you'll see that the cosine, which is the sine of this, is the same as the cosine of this, right? So that's what you get there. Also, because of another interesting, curious property of sine and cosine, note that if we have sine of minus x, that's the same as minus sine of x, and cosine of minus x is the same as cosine of x, right? So we're going to call the sine function odd, because when you take a negative value on the inside, you can just take it out. And we're going to call this even, because the negative values on the inside are swallowed up. Why is this true? Well, let's draw some things out. So if this is the angle x in radians, okay, what would minus x be? That would be minus x. And so sine, this is sine of x, this vertical distance here, and this is sine of minus x, okay? So sine of minus x is the same as minus the sine of x, because here we're above and now we have to be below, okay? That distance there is minus sine of minus x, okay? Well, cosine, on the other hand, when you do that, the cosine doesn't change at all, does it? Okay? Even if we were to consider an angle all the way out here, okay, you'll notice that the sine has to flip signs, but the cosine stays the same. Cosine will remain negative. All All right. Let's do an example where we use sine and cosine to actually solve a problem. Let's do an example where we use sine and cosine to actually solve a problem. And this problem seems fairly contrived. We're going to have a boat that starts at point P and moves in a perfectly straight line down a river for a certain amount of time to a point B. Okay. And then we're standing perpendicular to its travel. Somehow we figured out where that perfect spot to stand is. And this is 1,000 units of distance away. And then when we observe this later, we measure this angle A, and then we note that the cosine of the angle A is equal to 0.7. And the question is, what is the distance between the observer and the boat at this time? So what is the distance d here? Okay. So how do we calculate this? Well, we know that cosine of some angle is the same as the adjacent over the hypotenuse. The hypotenuse is the distance d. And we also know that that's equal to 0.7, right? So we may have used some small instrument to measure the cosine of that angle there. And so we can take 1,000 over d is equal to 0.7, multiply both sides by d, and with d is most certainly not equal to 0. And then we divide both sides by 0.7, so we get 1,000 over 0.7, which is the same as 10,000 over 7. That's our distance d. These problems really are this simple. There's not much more to it than this. And of course, this final section is where he talks about polar coordinates and how to convert them between each other. The formula that you're going to want to remember is this. So when we have coordinates a comma b, okay, then that's going to convert to polar coordinates r comma theta. And if we start with r comma theta, then to get to the rectangular coordinates, we're going to take r times cosine of theta and r times sine of theta. Okay? That's all there is to it. There's a final example here. Typically for theta, we typically choose theta such that 0 is less, no, we don't want equal to 2 pi. 0 is less than or equal to it, or it's less than 2 pi. But also you'll note sometimes we just choose theta will be between minus pi and pi, right? So the difference between these two systems is between 0 and 2 pi, right? That's 2 pi. And then between minus pi and pi, that means we'll go down to minus pi, and we'll go down to plus pi. So we'll just think of the bottom and top halves. And we like to use the positive negatives because of that sweet identity where sine of negative x is equal to minus sine of x and cosine of negative x is equal to cosine of x. It's a sweet identity to use when we can. Okay. So in this final example, we have a, b such that a squared plus b squared equals 1. We can always find the number theta such that a equals cosine theta and b equals sine theta. So we have a comma b such that a squared plus b squared is equal to 1. And so we're going to find that a is equal to cos theta because the radius is 1, and b is equal to sine theta. Okay. Therefore, the point which has rectangular coordinates a comma b is the same as cosine theta, sine theta, which is just the coordinates, the polar coordinates 1 comma theta. So that's the same point described there. And there's really not much more to mention beyond that. I hope you guys enjoyed this section. The homework problems, there's quite a few of them. They should feel uncomfortable. So frequently refer back to the definition of sine and cosine as you do these exercises. If you have any questions, be sure to leave them in the comments below. I hope you guys enjoyed this video. Take care, and bye-bye. Thank you for watching this video on Sergey Lang's Basic Mathematics. You can find the series on the left, and on the right you can click to support my channel. Thank you very much. Bye-bye.